All right, here's my video that I'm going to do for projectile motion. So we've already discussed about lap 1 and lap 2. Now, projectile motion, I like doing it after those past 2 laps because this is the combination of the two. An object is in projectile motion, so this is very important. They have to follow these conditions. A of x horizontally, you are not accelerating. You're still moving, your velocity is not changing in the x direction. In the y direction, you're traveling with only the gravity caused by, or the acceleration caused by gravity, which I'll round to negative 10 meters per second squared, but this is where, it's actually negative 9.8. So under these two conditions, this is projectile motion. If an object is not traveling with this very specific nature, then it's not projectile motion. If there's friction, it's not projectile motion. When we do this because it's easier to work these problems first without kind of any of that friction and stuff. So real quick, I've split up the two directions. Horizontal is x, vertical is y. What I'm about to draw for you are the graphs for an object. When an object does travel, it travels in this downward parabola shape. No matter where it's at, essentially its acceleration is always pointed down. And it's always the same amount. It's always that negative 10. So this green arrow is acceleration. As far as its horizontal velocity goes, it's always to the right here. It should always be the same amount. So purple I'm drawing here is its horizontal velocity. And what ends up, the only thing that really changed is this object's vertical velocity. I'll draw in red. I'll make it pretty big. So let's say this is it. However much smaller it's going to go here should be like subtracting this green arrow from it. And eventually we get to a point where it's not even moving vertically at all. And then it gets bigger on the way down. All right. Let's say you lost 5 meters per second going up. You'll gain that much when you reach the same height on the second half here. All right. So horizontal velocity stays the same, acceleration stays the same, and acceleration's always down. No matter where you are, it's always down. If it wasn't down, you would not form this downward parabola. All right, x versus t, or the x direction, it's actually just simple constant velocity scenario. So x direction is very straightforward. The y direction can be, this is where it differs. Y versus t, if you imagine throwing an object, this is what this graph will look like. So in this case, this is a perfect parabola. Object's going up and then back down. It's slowing down on the way up and then speeding on the way down. For vyt, to show this, I would go down in the positive and then keep going down into the negative. The slope here is g, which is negative 9.8 meters per second squared. So the a of y will be negative 9.8 meters per second squared the whole time. Now, as far as this midterm is going to go, we're not going to give you all the hardest problems. I would say either expect this symmetrical parabola or one where you're shot off horizontally. Why that's important? So this graph would look like this, and this would only go up to the halfway point. Why that's important is we are saying our v naught y is 0 in this circumstance. And that solves a lot of problems. Why is that? Let's write out all the equations that matter for this situation. So for the x direction, I only have one equation. X is equal to x naught plus v naught xt. And just so we're clear, v naught x and vx are the same. So if you find one, you find all the velocities. For the y direction, we have 3. Y is equal to y initial plus v naught y. T plus 1/2 gt squared. Remember, you're going to have to keep track of negatives, like g's equal to negative 10, so make sure you plug that in. V naught y, sometimes positive, sometimes negative, or sometimes it's 0. In these horizontally shot problems, a lot of times this term becomes 0. Not always, but if you're given shot from horizontal. All right, another equation that might look familiar. The slope equation from acceleration, except this time the acceleration is always g. And then this last one, y'all are used to this, sorry, 2g delta y. All right, so these equations, you've seen them before. These are the equations that came from constant velocity and constant acceleration, but I've replaced some terms. The most important variable is v naught y, because you need it all the times. In acceleration, it was v naught y and acceleration, but what's nice is all these g's are always given. You always know g is -10, so these problems work out. My suggestion is when you guys actually study for this stuff, I would practice these kind of problems, just two of the big problems, the full parabola ones and the horizontally shot parabola one. Just going back to your midterm review, if we go all the way down to like this cannon problem, here, this is a great example. I think what gets kids is sometimes they write out the equation and they just stop working because they're like, I don't have enough material here. But if you ever get like 0 times something, you know all of that's 0. And that's what happens in this problem. You try to solve for time, you write out this equation, and you think, oh, I don't have v naught y, or I don't have t, and there's t in 2 spots. How do I get this? Well, when you work the problem, you realize it's like -230 plus 0 or equals 0 times t plus 1/2 -10 t squared. Well, look at this, 0 times t, that's always 0. So these things work out on their own. All right, I'm going to leave it there and maybe 1 or 2 more videos to describe forces.